Hi, today my group will talk about Raman spectroscopy and its role in forensic science. Raman spectroscopy is a vibrational spectroscopic technique that identifies substances based on their unique molecular fingerprint. It is a rapid and non-destructive analytical method and requires a little sample preparation, making it highly suitable for forensic analysis. Because the sample remains intact after testing, valuable evidence can be preserved for further examination. The basic principle of Raman spectroscopy begins when a laser beam is directed into the sample. The light will interact with the molecule, causing them to vibrate and scatter the light. Small portion of the scattered light will change in energy, produce a Raman spectrum. So this spectrum acts like a molecular fingerprint and allows the scientists to identify the substance accurately. In forensic science, Raman spectroscopy has many important applications. It is commonly used for drug identification, explosive residue analysis, paint and fiber examination, ink analysis, biological sample analysis, and trace evidence analysis.
Now I'm going to talk about the sampling in forensic Raman spectroscopy. Raman spectroscopy is a non-destructive analytical technique widely used in forensic science. Although Raman spectroscopy can provide highly specific molecular information, the reliability of the result depends heavily on proper sampling. Therefore, sampling is considered one of the most critical stages in forensic Raman analysis. First, Raman spectroscopy can be applied to a wide range of the forensic evidence, including blood stain, textile fiber, can chip, gunshot residue particle, narcotic substance, and also document inks. Since these materials have different physical and chemical properties, different sampling methods are required for each type of the evidence. Next, the first problem is sample heterogeneity. Different regions of the same sample may contain different chemical compositions. As a result, a spectrum collected from only one location may not represent the entire sample. This can lead to non-representative spectrum and unreliable forensic comparisons. The second problem is contaminations. So during sample collections, contaminants such as dust, skin oils, swab, or glove may introduce additional Raman peaks or fluorescent interference. This can make spectral interpretations more difficult and may obscure important diagnostic signals. The third problem is sampling bias. For example, investigators may unintentionally select one visually clean area or collect too few spectra. This can result in misleading forensic interpretations because the analyzed region may not accurately reflect to the overall evidence. The fourth problem is the laser-induced damage. Excessive laser power may alter the sensitive forensic material, causing the peak shift and also reduce reproducibility. Consequently, the acquired spectrum may no longer represent the original sample. This sampling problem directly affects the forensic interpretations. As shown in the flow diagram, sampling error may produce poor quality Raman spectra, leading to inaccurate identifications, false source attributions, and ultimately unreliable forensic evidence. So several solutions have been proposed to minimize this problem. Raman mapping can reduce the effect of the sampling heterogeneity by analyzing the multiple locations across the sample. The use of personal protective equipment and procedural blank can minimize the contaminations. Multiple sampling regions and replicate measurements improve representativeness and also reproducibility. In addition, the laser power should be carefully optimized to prevent sample damage.
In this section, I will present the instrumentation of Raman spectroscopy. Raman instruments are designed to detect vibrational transitions by measuring a very small frequency shift in scattered lights. In general, the instrument consists of three main components, which are laser excitation source, wavelength selective octave, and a sensitive detector. In a typical setup, a monochromatic laser is focused onto the samples, so when the laser interacts with the samples, most of the scattered lights is elastic scattering, but a very small portion of inelastic scattering, and this contains the Raman information that we need. This Raman scattered light is collected, usually in backscattering geometry, and directed into the spectrometer. Inside the spectrometer, a diffraction grating is used to separate Raman shifted lights according to their wavelength. At the same time, notch filters are used to suppress the strong Rayleigh scattered light, which would otherwise interfere the Raman spectrum. The signal is then detected by a cooled CCD detector because Raman signals are naturally very weak and require low noise, a high sensitive detection. For micro-Raman application, the system is coupled with an optical microscope. This allows the laser to be focused into the micron scale spot and also improve the collection of the scattered lights. As a result, micro-Raman provides a high spatial resolutions and can be used for point analysis, line scanning, or even area mapping of the heterogeneous samples. Beside the conventional system, a more advanced Raman platform has also been developed. One important example is the surface-enhanced Raman spectroscopy. In this Raman spectroscopy, the silver or gold nanostructure creates electromagnetic hotspot that can be enhanced the Raman signal for about 10 to the power of 4 to 10 to the power of 8 times, making the method highly sensitive. Another example is the tip-enhanced Raman spectroscopy, or TERS in short, where a metal-coated AFM or SDM tip can act as a nano antenna to provide a chemical imaging at nanometer scale resolutions. Modern Raman instrumentations also include software and advanced data analysis, since Raman bands are often weak and overlapping. Steps such as baseline correction, noise suppression, and multivariate analysis are needed. More recently, deep learning models have also been applied for spectral preprocessing and classifications, helping to improve signal quality and speed up identification of materials, pathogens, or even disease states. When developing a Raman method, important parameters such as excitation wavelength, sampling configuration, laser power, and integration times can affect the balance between signal strength, fluorescent background, and sample damage. For example, near-infrared excitation at around 785 nanometers is commonly used because it reduces fluorescence while still giving acceptable sensitivity. Finally, after optimizations, the method must be validated to ensure it is fit for purpose. Validation is typically based on criteria such as specificity, linearity, accuracy, precision, and robustness. However, Raman spectroscopy still face limitations such as weak intrinsic signals, fluorescent interference, and instrument drift, so regular calibrations are essential. Overall, the Raman instrumentation has developed from a basic laboratory optical setup into a more advanced, sensitive, and field deployable analytical platform with wide application in science, medicine, and industry.
My name is Kesha, and I'll be presenting about data interpretation and theoretical limitations in forensic Raman spectroscopy. So, Raman spectroscopy is widely used in forensic science because it provides highly specific molecular information. But then, the interpretation of Raman spectra is not always straightforward, as it can be influenced by several factors such as interferences, artifacts, matrix effects, and also theoretical limitations, and all of this can affect reliability in forensic applications. So one of the main issues is interferences, which is mainly caused by fluorescence. So fluorescence will occur when certain materials produce a strong background signal, and it can overwhelm the weak Raman scattering signal. So this is commonly seen in colored substances, biological samples, and also contaminated evidence. And as a result, important Raman peaks may become hidden. This will make it difficult to identify the substance. And also in addition, contamination from environmental sources such as dust, soil, skin oils, or cosmetics, as well as collection materials like swabs or gloves, can introduce extraspectral peaks that interfere with interpretation, especially in trace evidence such as gunshot residue or fibers. Also, another important factor is also artifacts. So artifacts are signals that do not originate from the sample itself, but it originates from the instrument or experimental conditions. So as an example, some artifacts could be detector noise, calibration issues, or instrument drift that will cause artificial peak shifts or intensity changes. In some cases, excessive laser power can also damage sensitive samples, such as inks, which lead to chemical changes that distort the spectrum, and it will also overall affect the forensic interpretation. Next is about the matrix effects, which also play a major role in forensic samples. The analyte is often mixed with other materials such as binders, polymers, fabrics, or cutting agents in drug samples. So these surrounding substances can dominate or overlap the Raman signal, and it will make it difficult to isolate the compound of interest, and it often requires advanced chemometric analysis. There's also something called theoretical limitations. So Raman spectroscopy typically analyzes only a very small area of sample, meaning that heterogeneous materials such as fibers, layered paints, or fingerprints may not be fully represented by a single measurement. So additionally, the Raman effect is inherently weak, which produces a low signal intensity. So this will make it less effective for trace level evidence. And this also increases sensitivity to noise and interference. And finally, sampling bias can occur if the laser is poorly positioned or insufficient replicate measurements are taken, which can reduce classification accuracy in forensic comparisons. So in conclusion, while Raman spectroscopy is a powerful forensic tool, its reliability depends heavily on controlling these limitations. So there are some techniques that can be used, which are Raman mapping, improved sampling strategies, and also surface-enhanced Raman spectroscopy, which can improve accuracy and reduce uncertainty in forensic interpretation.
Let's begin with the regulatory integrations. In forensic chemistry, analytical results must meet a criteria that is admissible in court. So under the framework of SWG and also ASTM, the analytical methods are divided into three categories, which are A, B, C. Traditionally, Raman spectroscopy are designed as a category A technique because it gave a direct result, and which is the molecular fingerprint. However, this is not a fixed stated in all crime scenes, because as if there is a field portable or handheld device utilized a restrict spectral library or the lower optical resolutions, it will downgraded into category B or C. To be mentioned, category ABC technique cannot stand alone itself for the crime scene or analysis. It need to combine with other category technique. For example, category A with category B to identify the sample. To overcome physical barrier like weak inelastic scattering or matrix fluorescence, there are advanced Raman hardware that are used, which are SERS, SORS, SERDS, and so on. So here in the poster, I mentioned SERS, that is stand for Surface Enhanced Raman Spectroscopy. So it will have two key phenomenons, which are the electromagnetic enhancements. They will create a localized electric field, while the other one is a chemical enhancement. So it will occur the charge transfer mechanisms. These two phenomena will amplify the weak signal by staggering factors of 10 power of 4 to 10 power of 11. So this SERS is enable the detections of the trace target method down to the part per billions level. Other than SERS, there is SORS that I mentioned just now. It allows to scan through opaque packaging, or the SERDS can cancel out the destructive background fluorescence. Last but not least, for my future recommendations are for the utility of Raman hardware. First of all, standardizing body can establish a quality protocol for SERS substrates to produce a highly uniform and stable nanoparticle array to eliminate the spectral variability for the core room. Secondly, the hardware developer can combine the different Raman hardware together into the one unit. For example, SERDS with SORS or SERDS. So it can improve the utility and advancements of the Raman hardware. Furthermore, they can build open access or cloud-based to ensure that the data inside is continuously updated, so that everyone can refer to updated information. Furthermore, they can also embed the chemometrics tool like PCA, PRSDA, and also CNN directly into instrument framework, so they can automatically deconvolve the mission and strip away the background noise, and also eliminate the human interpretations bias. Lastly, the international body must draft a clear legal validation protocol for this automated system, so that it can safeguard the chain of custody against the tampering. So in conclusion, Raman spectroscopy is indispensable tool in forensic field. To avoid the physical barrier like the weak signal scattering, they can use other Raman spectroscopy or combine them together, such as SERS, SORS, and so on, to limit the weakness. But bear in mind that the reliability of the spectral integrations is heavily depends on the systematic sampling design. So for the future recommendations, the standardizing body and also the international committees can create a clear protocol, quality protocol, and also the clear digital chain of custody to limit or minimize the human interpretations bias. Besides that, they can also embed the AI technology to help humans to interpret the result and minimize the error as well.